You want me? Okay.
I just did it. All right. I'll put on broadcast. Spotlight. Ta-da! Everyone can see you.
Okay, why don't we get going, Colin? It's 11:04, and yeah.
Yep. Okay. Give me a little bit of time. Ooh, share screen. All right. Cool. All right. So, good day, everyone. Thanks for joining our session again, 2-minute session again today. Thanks for staying with us for the past 3 months. It has been a long time, and we still have quite a lot of people. I mean, about, as I see now, about 100 people. So I'm going to say the same thing the same thing again as I do say every time. So like, if you're new here, please subscribe to the mailing list so that you can get like information about our future events. And also like I've talked actually like this I've talked to Bob. We have some plans about like changing some details for our Zoomina sessions, but we have not finalized it yet. Like we might be thinking of like doing it on other day or making a bi-weekly event, but stay tuned. I mean, like this is, so subscribe to our mailing list so that you get the latest information. And if you are interested to in listening to our previously recorded sessions, like these videos are recorded and they are actually posted on our group website. Don't worry about like taking this down. I will copy and paste it in the chat room later so you can look at it. And if you have any questions, use the Q&A function to ask the questions like anytime during your talk. Don't put it in the chat. And also like if your question is too long and if you feel like asking the questions verbally, feel free to raise your hand. So that either our IT support, like Michael Martini or I will like give you the permission to talk, and then you can ask your questions yourself. And finally, all the Q&A sessions, like in the past sessions, they were noted down and I put it in the Dropbox. So feel free to look at it, and you can also like comment on it. So this is like one of the features that allows you to have a post-Zoomina discussion. So I will copy and paste this in the chat room, and I will now pass the session to Bob so that he can introduce our speakers today. Bob, please.
Okay, so today we have two really excellent speakers. Scott Carnahan from Iowa State. He's a PhD student with Aaron Rossi, and he will be telling us about some DNP experiments using, I think, gamma radiated crystals to generate a polarizing agent in situ. And then the second speaker is Professor Marina Bonatti, who is from Göttingen, Max Planck Institute in Göttingen, and she will be telling us about fluorine-19 DNP in solution, as well as some indoor experiments. So Scott, why don't you proceed? So the virtual floor is yours, okay?
Great, thanks, Bob. I'd like to thank Bob and Kong for giving me this opportunity to present some of my research over the past year. I'll be talking about 2/3 about previous published work, and then the last third should be new unpublished data. So hopefully you guys can see some interesting new stuff. So here's our DNP lab over in Ames laboratory that we have access to. It's a standard 400 megahertz, 263 gigahertz commercial Brooker NMR setup. Currently the space is under renovation, and they're putting together a NMR center at the Ames lab. Hopefully this will be finished soon, and we're all pretty excited about this. Just a quick recap on DNP for organic systems, just to kind of guide where I'm going to be talking today. So you have some polarizing agent inside your solution that's on top of your crystal or particle or whatever you're doing DNP on. You're going to irradiate it with microwaves. This is going to cause electron-electron spin flip and simultaneously flip a proton spin in the solution. This is standard cross-effect DNP. If you have crystal, then what's going to happen, proton-proton spin fusion is going to move that hyperpolarization from the surface, from the solution to the surface of your crystal, and then further proton spin fusion will move that into the core of the material. However, if you don't have any protons in the core of your material, such as systems like inorganic particles, you may struggle to get polarization into the center. So back in 2010, Anne Lesage and Lyndon Emsley pioneered DNP surface enhanced NMR spectroscopy, which really utilizes this technique of you taking the polarization from the solvent to the surface. And they've been able to do some very exciting and amazing things about surface characterization. However, since there's no protons to move that spin diffusion closer into the core, there's a struggle to get that hyperpolarization to the core, if that's what you want to see. More recently, the group from Lyndon Emsley has used that same technique to get polarization to the surface, and then use slow heteronuclear spin diffusion to hyperpolarize the core of these materials. If you saw Sneha's talk earlier in the webinar series, she did talk about this a bit. And you can, and here they've been able to show this for silicon, tin, phosphorus, a bunch of different heteronuclei. But one thing you see is that the DNP enhancement that you get at the surface is significantly higher than you get for the core when you do this relayed DNP. So one other technique would be to introduce your radicals instead of in a polarizing agent in the surface, but actually into the core of the materials. This has been done a number of times using gadolinium, manganese, chromium as the doping agents. But our idea was to create these radicals using gamma radiation. So then we have radicals inside the core, and we can do direct DNP and directly polarize the silicon in the core of these materials. So using gamma radiation or neutron radiation to create radicals for DNP is not necessarily a new idea. Some of the earliest DNP experiments use these radiation damaged samples. So our idea was to kind of take that initial idea and bring it to high field NMR using MAS, as well as doing it at more moderate temperatures, because a lot of these were done at low field, static, and at ultra low temperatures. So one of the things that we do is we track the EPR signal so we can measure and study the radicals before and after gamma radiation, and with different gamma radiation doses. So if we just look at, here's the signal for quartz. Before radiation has a very small concentration of radicals. And in fact, pretty much everything I've ever put in an EPR spectrometer just has some background radicals that you're able to see. And then after gamma radiation, there's a drastic increase in the amount of radicals. And I was thinking to myself, what other system after gamma radiation is there this huge grow in size? And if you think to Bruce Banner, after being gamma rated, he becomes the Hulk. I actually messaged Marvel and I asked if I could use a picture of the Hulk in my TOC graphic, but I never heard back, so it didn't happen. The gamma radiation was performed at Brookhaven National Lab under the advisement of Jim Wishart. And just kind of a show of what's happening here. So we take, the samples are held in just traditional scintillation vials. They're clear, white cap. And then, so these are the sample holders during gamma radiation. And you can see that with increasing gamma radiation, as we go left to right across this picture, you can see that more gamma radiation creates more color defects, which are radical defects. So you can really see the effect of increasing radiation. And if you look closely, you can kind of see some of the glucose powder in there or quartz tube. And I'm going to be talking about these samples a bit later on. So what Jim does is he has the samples kind of stacked cylindrical into a column like this, and then he lowers them into a cylinder where there's cobalt-60 gamma radiation evenly from all sides. So the samples get evenly gamma radiated. I'm going to be talking a lot about quartz because it has some very special features for NMR and EPR. It has some very cool properties. So even as far back as the 1960s, this is one of the most well-studied systems by EPR. So gamma radiation and neutron radiation give the exact same EPR signature for fused quartz. And what's happening here is quartz has this silicon with a tetrahedron of oxygen around it. And during the gamma radiation process, the bridging oxygen is removed, and then there's an electron sitting on a silicon. This is E prime vacancy or E prime radical or an oxygen vacancy. So I'm going to walk through a bit of our actual data now. After gamma radiation, we had a 0.3 millimolar radical concentration. So this is kind of in comparison to if I'm doing standard cross-effect DNP with TechPol TCE, what I get is, when I make the solution, it's typically 16 millimolar radical solution. So we get significantly less radicals in our sample than when you do the solution. When we do a field sweep, we're able to fit this field sweep to a solid effect profile. So we're pretty confident that with a low radical concentration and the splittings between the positive and negative maxima, we're able to say that the DNP is happening through the solid effect. When we do NMR, we're getting these large enhancements, and we get enhancements up over 400. If we use longer delays, you can see 10,000 second delay is about 3 hours. So we're waiting 3 hours to get one scan. Well, it kind of seems like a long time. Like I said, quartz has some special properties that has really long delays or relaxation properties. One of which is that the refocused T2 or the T2 prime, when I do CPMG acquisition, I'm actually able to acquire echo packets out for an entire 20 seconds, which is limited not by the sample system, but actually by the Brooker software. You can only acquire for about 21 seconds. So I'd be really interested to see how far out we can actually acquire things in the time domain here. Recently, Fred Perrat over in Ames Lab had a project where he calculated DNP for a number of different systems, one of which was gamma radiated quartz. And what's kind of special is he was able to reproduce the DNP enhancement that we were able to get experimentally. And he used a system of about 5,000 silicon-29 spins, which for an ab initio system is extremely large. And what you kind of see with his calculation is that silicon-29, they're in close space to electrons, get very well hyperpolarized. And then as you get further and further away, it reaches about an equilibrium. And the average DNP enhancement is what we're going to see when we do our NMR experiment. As a part of this project, we measured electron and silicon nuclear T1s at 100K. And this is where we kind of see the special properties of quartz. So at 100K, we see that the electron T1 is orders of magnitude longer than that of standard nitroxide radicals. And this is one of those reasons why you see that we're able to do some special things with it. In addition, the silicon nuclear T1 is 180,000 seconds, or 50 hours, or more than 2 days, if we wanted to try and do something quantitative. It makes this extremely difficult. So that's why waiting 10,000 seconds or 3 hours for one scan on the time scale of the silicon T1 is still really not that large. This is an extremely long T1. One of those things we can do with having a long T1 is we can go to higher temperatures. So if we just measure out to like 200K, we do still get enhancements, though there is a slight decrease. But if we go to some really long delays, so we kind of maximize our enhancements, we're able to get DNP enhancements of about 150 up at room temperature. So this might open the door to some other options for room temperature DNP. What can we do with this large enhancement we're getting? Well, one of the kind of litmus tests for how well our DNP is working is to perform a silicon-silicon inadequate. So this experiment requires two silicon-29s to be bound together in a SiO-Si kind of spin system where they have this bridging oxygen. But what makes this experiment kind of special is the fact that silicon-29 is only 5% abundant. So the probability of having two silicon-29s in space next to each other is extremely low. So this really hurts the sensitivity of your experiment. And what you can see is that we're able to get this inadequate spectrum in essentially just an overnight experiment. While it's not the most interesting experiment, there's only one site in quartz, and you can just see autocorrelation. It does demonstrate the power of the DNP enhancement that we're able to get. Like I said, there's some other samples we're able to get this to work for as well, one of which is gamma radiated glucose. There's a couple different possible structures or proposed structures for gamma radiated glucose, both of which have the radical sitting on a carbon center. One thing we can see is that the EPR spectrum for glucose is much more broad than that of quartz. There's some hyperfine coupling, a larger G anisotropy. We also have a higher radical concentration as well, about 10 times higher than that of quartz. When we do our field sweep, we also see that it's much more broad. We're only able to get a partial field sweep for this one. And we can see that there's a broad match condition. And between the broad field sweep profile as well as the higher radical concentration, we're thinking that this might be through the cross effect, but it's a little bit harder to tell. If I just compare glucose impregnated with TEC-Pol TCE and do DNP that way versus a couple different gamma radiation doses, what we see is there is some slight broadening around the base of the peaks due to the gamma radiation, however, even though we have like some broadening, you can change the amount of dose to limit the broadening if that's an issue for you. In addition, what we see is that the actual sensitivity that we're getting from the gamma radiated samples is significantly higher than that when we get when you do DNP using TEC-Pol TCE. And TEC-Pol TCE of microcrystalline solids is a well-founded system that works in many different samples. But we're able to show that we're able to get similar or better overall sensitivities using gamma radiation on glucose. And this is probably due to the fact that we have a much shorter proton T1, in addition with getting decent enhancements. So before I show this picture of the vials and the vial caps, and you can see the irradiation damage. So one thing I did was I just took a vial cap, I ground it up, and I did DNP on it. So with essentially zero optimization, no field sweep, nothing. I just took one vial cap and I didn't try and optimize gamma radiation amount. We were able to get a small enhancement. So this kind of says like I can just take something and we might be, especially if it's a polymer, I can just take some and gamma radiate it and run it, and I should be able to get some sort of enhancement. There's still room for a lot of better optimization here. I took one that had 0.2 millimolar, which is one of actually over here on the left side. I did not take one of the higher dosed samples, so there's lots of room for optimization here. In addition, we did gamma radiation of cellulose. And you can see we had a very low radical concentration in cellulose. And even though I only had a partial field sweep profile, we were able to hit a position where we're able to get at least an enhancement of 2. So there's still more that can be done here, trying to increase radical concentration or doing a better, having a more thorough field sweep. We might be able to drastically increase this for some other samples too. The field sweep is kind of the time-consuming part right now because we just have a standard Brooker NMR magnet that I'm changing the field on, so it's a little slow. We're able to get radicals in a bunch of other samples. I don't have time to really talk about a ton of this now, but one that I'm going to talk about in a bit is borosilicate glass. So the sample vials, right, we saw they changed color, but also in some other borosilicate glasses as well. And we were able to get high radical concentrations in these, but DNP didn't work, we believe, because there's this high G anisotropy, as well as a fair amount of hyperfine coupling to boron 11. So these are a bunch of samples that aren't published that we didn't get to work, which is potassium phosphate or silicon phosphate glasses, hydroxyapatite, which is a mineral in bones and teeth. So we attempted DNP and we didn't get them to work for various reasons. We're still trying to figure out exactly why for some of these. One other thing we tried to do was reduce particle size of quartz. So we had Xun Wu from Wenyu Wang's group synthetically make smaller quartz nanoparticles of 150 or 210 nanometers, 70 nanometers. And what we saw, it was hard to get radicals to stay in these very small samples. We think we know why, but we weren't able to get it to work. So we thought, what other way can we reduce particle size? which was, instead of synthetically making them small, let's ball mill a large sample. So when we did that, what we actually found was we actually had more radicals after ball milling than we did if we just gamma radiated the sample. So particle size wasn't quite as small as we were hoping, but what we did get were these large influx of radicals. And we were able to do DNP with these. We put it in, and you can see that it has a fairly narrow positive maximum. And when we do, we were able to even test several different ball milling procedures to try and optimize this. And we were able to get up to a maximum of a DNP enhancement of around 120. And this, as you can see, this is a bit lower than the 400 we got through gamma radiation. And we think that's because gamma radiation caused a more complete or more evenly dispersed radicals through the sample, whereas we think ball milling is creating kind of clusters of radicals, which makes it a less efficient DNP polarizing agent. So I talked a little bit about the borosilicate vial, right? So the gamma radiated vial gave this very broad spectrum, whereas, which is this oxygen-centered radical near a boron. So boron-oxygen hole-centered radical. And what we saw when we ball milled it was we got a completely different type of radical, which is an oxygen vacancy radical. So by changing the method of introducing these radicals, we're able to make different radicals. As we can see, we got the exact same radical in the vial as in the ball milled quartz. We weren't able to get DNP on the gamma radiated vial. Maybe we're going to be able to get it on the ball milled vial. So this is ongoing. We had to kind of halt research due to COVID. So this is what we're working on right now. And hopefully over the next few months, we'll be able to get some more definitive data. One last project I'm going to talk about, which is a bit of a step sideways, is with our collaborators in Victor Bolema's group in Ames Lab. And what they do is they take tungsten selenide and molybdenum sulfide, which are layered 2D materials, and they're able to mix them by using ball milling. So they use ball milling, the layers get interspersed in between them, and then they do this annealing step at 1,000 degrees Kelvin, or 1,000 degrees Celsius to fuse the sheets back together. And I was doing traditional TechPol TCE solution DNP on these, and we were getting good enhancements of the solvent, and I was getting selenium DNP spectra. And then the moment we went to the ball milled sample, we got no enhancement, and we saw that the proton T1 skyrocketed. After the annealing step, we then saw that we're able to get solvent enhancements again, and the proton T1 became much more reasonable. So the red flag for us was the proton T1 shooting up, which means that the TechPol in our solution was probably getting eaten up some way. So we tested this by EPR. Tungsten selenide by itself really didn't show much radicals concentration at all. But then after ball milling, we see that there's a large amount of radicals created with an extremely large G anisotropy. And then after the annealing step, the G anisotropy shrunk, as well as the amount of radicals also reduced. So we're really starting to understand what this harsh ball milling procedure does to samples. And this is something we want to look into further. So kind of in conclusion, what did we do? We showed gamma radiation and ball milling can create radicals in both organic and inorganic materials. We're able to track the radical concentration and the radical creation by EPR extremely easily. And in even some of the better cases, we're able to perform DNP at MAS on these samples. So what are we kind of looking for that kind of still needs to be done? Well, on some of these samples it didn't work. It's probably because they had a high G anisotropy, or if there was a large presence of abundant quadrupolar spins, which create these hyperpolarization sinks, which kind of take the polarization away from the nucleus we want to look at. High field EPR would really be effective in helping us understand the radicals, because I'm doing X-band EPR, which is 9 gigahertz, and then I'm doing DNP at 263 gigahertz, and there's a little bit lost in translation there. So we have done a little bit of high field EPR, but routine use of high field EPR would really make this go probably a lot easier. And one of the main, so for a lot of these samples that didn't work, pulse DNP techniques would probably be very effective. So Kong and Bob both are pioneers of this, as well as Songy Han, Xander Barnes. And if we were able to use some of these pulse DNP techniques, we're probably able to get some of these samples with large GN isotropies to work as well. With that, I'd just like to thank all the people that helped out with this, specifically my boss, Aaron Rossini, the rest of the Rossini group, as well as a lot of my collaborators in Ames Lab and at Iowa State. But I'd specifically like to point out Jim Wishart at Brookhaven National Lab for doing all the gamma radiation for us. And I'd be up for taking any questions. Thanks.
All right, thank you, Scott, like for a very interesting talk in showing like a new way or another approach to make like gamma radiated like radicals, which could open up a new field for endogenous like DNP. That's very nice. Thank you. So like for participants, like feel free to type your questions on Q&A, which I will deliver to Scott. But before we begin that, I will also like letting you some time to type your question. I have a quick question. So you say like you occasionally use like high field EPR, like higher than X band. So which field do you go up to, like Q, W, or higher?
So we had 260 gigahertz done at the high field lab in Tallahassee for quartz, glucose, and the gamma radiated borosilicate vial. So we do have a little bit of data in these systems, but
all right,
for it to be more routine would be better.
Was it more like a CW EPR or a pulse EPR that you did?
It was CW.
It was CW.
Yep.
Because I'm just curious, because like I think when you show like the T1E, and then like I think for the quartz it has like a millisecond like T1E, and then like I also remember that Marina told us like last year, she said that on some of the samples that she did the EPR on, she found that the T1E actually decreased by a factor of 10, an order of magnitude, when you go from the, XQ to 263.
Yeah. That's
Marina,
one thing we don't know. We did all the pulse stuff at X band. So
yeah, and this is something very, very interesting. Maybe Marina, you want to comment on your finding?
Yeah, I mean, this is. Can you hear me?
Yes, we can.
Yeah.
Yeah. So well, I think this is something that we just observed, and it's reproducible. It's a low temperature. Yeah, so I should point out we observed that between 10 K and 80 K, and we have not now tried to give a quantitative explanation of it, but in principle, it's this is our observation, and one should consider this, in principle.
Is this something general that you observe this on the organic radicals as well, inorganic, or I think you say that this is true for RNR. Is it true for nitrox?
So we saw that on BDPA and nitroxide also. But we did not publish a systematic study yet on that. So I would like to be a little bit careful.
Okay. But it's true that, I mean, like as Scott and everyone.
It's true, yeah.
Yeah, we should look into, there could be a possibility in the loss of translation when you do from 9 and try to interpret something at 263, but high field EPR. And then Bob is a very, very strong, but he always encourages people to do high field EPR. And then Bob will say, right, Bob, if you want to comment, if you want to sell your 140.
Oh, well, yeah, I mean, some of the spectra at 9 are already broad. It could be due to hyperfine coupling, but it could also be due to G. So like the spectrum of the gamma irradiated glucose. I was going to ask you what that is.
On page 24, I think you have a small peak on the left.
Yeah, well, there's a,
yeah, exactly.
Well, there was the first spectrum he showed. Yeah.
Down here on the left.
Yeah. I mean, that looks like a very complicated radical with a lot of hyperfine coupling. So, yeah. And it could broaden out significantly at higher magnetic fields. So, I mean, in order to understand the DNP, you really do need the EPR for that. Yeah.
Yeah, we use it just kind of as a guide, a place to start.
Yeah.
But then there's a bit
No,
of
you
just
have to
kind of
do something.
hoping at once you get to the high field that
Yeah,
you
yeah.
find the right peak.
All right, maybe we should ask some questions. We have like 12 questions now.
Yeah.
All right, so like the first question from Gabriela, how do you make sure of the homogeneous distribution of the radical species by gamma irradiation? How long live are the radicals?
So this was a question we had for our collaborator, Jim Wishart, and he said that it is going to be very well homogeneously distributed, mostly because when we have it gamma radiated, we just have a thin amount of sample in the vial, and the gamma rays are very penetrating. They're going to be able to get through the particle sizes fine. So that's not something we need to worry about too much with gamma radiation.
Okay, and then the next question from John, how does the gamma irradiation approach compare to the beta irradiation approach that's popular in the spin polarized nuclear target production?
That's not something I'm totally familiar with. I guess I haven't seen EPR from those systems.
You tried neutron irradiation?
We have not yet tried neutron. We know that it works just because you can find EPR of neutron irradiation. We'd also like to try E-beam irradiation, so we're trying to find, but you have to spend a couple $1,000s to get things E-beam irradiated. So it's kind of a cost thing.
Okay.
Yeah.
All right. Next question from Raj. What are the limitations on the kind of samples you can use this technique for? Without
yes. So one of the things we've kind of realized is that glass samples might be one of the most effective, just because you're looking for things that you can't do traditional DNP with. So you want things that have larger particle size, so not nanoparticles, but then things that are also going to trap electrons. So glass samples, polymers seems to be very effective as well.
Okay. Yeah. Next question from Jeffrey. Have you found a linear relationship between the R1H and the concentration of radicals created by gamma irradiation?
I'm sorry, what was the first part of that?
Oh, so like have you found a relationship between like the T1 relaxation and the concentration of radicals?
I don't have a direct plot, but I can say that as you increase radicals, T1 goes down. I'm trying to do a more systematic study of that right now, where I have a large variety of samples with a lot of different time or gamma radiation points, but I'm still working on that. Yeah.
All right. And then the next question from Snade is, how much does the enhancements change with respect to the radical concentration? So for quartz, the more radiation you can get in, the better. But there is a point where you saturate the sample and you can't create any more radicals. So the gamma radiation kind of annihilates current radicals when it forms new ones. So the most you can kind of get in, which we're at the max here, is better. And if I have less, then it's not working as well. For glucose, what we saw was there's kind of an optimal spot. If you go too much, you start getting lots of line broadening. So you want it lower. You want kind of a medium stuff, I think, a medium radiation amount for organic samples. Yeah, and you also show like the T1H is also very critical in determining how much enhancement you get.
Yes. Yep.
Next question from Daniel Lee. Oops. From the field sweep experiment, it doesn't seem like pure proto-solid effect that was observed.
I mean, well, like if we think back to my, let me pull up the field sweep real quick, at least for quartz. The issue is that I made this field sweep profile based off of this EPR spectrum at X band. So just kind of guessing how it should look. And so it's kind of a hand wavy way of putting it. You can see that the horns are, at the appropriate positions for the silicon Larmor frequency for solid effect, if you actually measure it out.
Mm-hmm. It doesn't look very anti-symmetric.
No, it does not.
Yeah, and also like perhaps like if you do it at high field, then you can resolve the hyperfine energy. Then with if you know like these values for the EPR for the radicals, then it's easier to predict it theoretically.
Right. It is not a professional fit. It was kind of done just to verify.
Yep.
Yeah.
And next question from Anonymous. Why does your cellulose peak shape looks slightly weird to him or her? Is there any effect?
So with some of these samples, there may have been, like one, this was kind of an old sample. So it's quite possible that there was some degradation during the gamma radiation process. This is something you need to be careful about, is I have seen in some samples new peaks come in. So you need to be careful that once you get to a certain gamma radiation amount, you are changing the crystal structure, right? You're making all these defects. So you do need to be a little bit careful about the amount of gamma radiation you're putting in. Also, going to low temperature can shift peaks slightly, things like that, I think.
All right. And due to time constraint, I will perhaps like take one last question.
Sounds good. And I can respond to the rest during the next talk.
Next question from Akshay Kumar. How much effective power on sample and the frequency of irradiation do you use for the gamma irradiation? Cobalt 60.
Power of the gamma radiation? Is that the question?
Yeah, I think so.
So the cobalt 60 source is just going to output however much it outputs. And all we can really vary is the length of time our sample spends in there, which then designates the dose. So depending on the sample, organic samples need a lot less dose than glasses like quartz. So we kind of choose the irradiation amount based on that.
Okay, all you can control is just like the time window for your.
Yep.
All right. Thank you very much for answering all the Q&A questions, and
yeah,
feel free like to type in like the answers. Like,
yep.
Sure.
And if people have questions, they can email me. I think my email is on the email that Kong sent out. So
the Q&A will be posted on our Dropbox, and then like feel free to look at it. All right.
Sounds good. Great. Thank you.
Our next speaker.
Okay, thank you, Scott, very much. Yeah, so the next speaker is Marina Bonatti from the MPI in Göttingen. And Marina has done some really beautiful solution DNP experiments using diode sources. And I don't know if you have a gyrotron yet, maybe someday soon, right? As well as some beautiful F19 indoor experiments. And that's what she'll be telling us about today. So Marina.
Okay. Thank you, Bob. So I will go over to screen sharing now. And I'll start my presentation. Oops.